split gen either takes a character or a list of characters. So then we can reuse that basic logic. Value t-type. Escape. Type char. Okay. Oh yeah. So what is the escape char here? So split S escape char on returns a list of substrings of S that are separated by literal versions. It's a little bigger. Separated by literal versions of on. Here we have commas, so it would separate at these comma characters. Consecutive on characters will cause multiple empty strings, and the result, splitting the empty string returns a list of the empty string, not the empty list. Yeah, so it would just print, or it would return that. Okay. So the escape character doesn't talk about, but I assume it's just. Now, what if there was another? Let's look into the implementation of that too. Go back enough. Here we go. I wonder why this chooses to be type agnostic. Why split is using generics instead of just saying string, instead of the type just being string on element string list. Let's see, why does base to implement split as versus string string, here we'll just do this, versus string is this the right? I want to look up the, go forward again. Let's copy this. And then, what here? Oh, wait. What split was I reading? I was reading, oh, escaping? Yeah, this one, escaping. Versus the one, the proper split would be here. Escaping, that's why I had escape character. Here's a list of substrings of S that are separated by on. Consecutive on characters will cause multiple empty strings in the result. Splitting the empty string returns the list of the empty string, not the empty list. And then, since we're here, let's just read this. Split on chars S on returns a list of all substrings of S that are separated by one of the characters from on. Okay. On are not grouped. Okay. So a grouping. So can you do a regex? I assume you can do regex with split on chars then. And you want to make sure that since they are not grouped, if you have a grouping of those characters, so if those characters sequentially occur within your string, then you're going to produce multiple empty strings within that list. Because essentially what you would have is let's say your string was well, we can have it just be anything. Just make it simple, and then when you convert it, let's say you pass in as your on would be let's actually do this right. So split on char, split on chars, and then our on would be what do you do that? Oh, chars list. Okay. So the so if we wanted to check and split on every addition and equal sign, this is how we would do that. But it's talking about with when you're providing multiple characters, they're not grouped. So essentially here we're providing a string that has these sequential. So what we're gonna end up getting, instead of getting this, this might be what you would expect if you used it. Instead of getting 2 A's in your list, you would actually get a empty string in between the 2 A's. Because this grouping is essentially being like evaluated twice maybe. So there's this empty string between these operators, and that result is seen within our list product. So I believe that's the case. I'm going to ask, why does base choose to implement split as generics instead of string? Base string is not implemented directly on string. Instead, it's implemented on a generic sequence like abstraction. So I guess you could use it somehow with a list. All right, so here's split gen again, and has that or type where we can either have Okay. So this less than sign means that it will accept any type that is within the subset of those types. And let's see. All right, so what are we doing here? So is delimiter maybe? Delimiter match on. Yeah, so we're matching, is it a single char character or is it a list of characters? And we so this returns Boolean equal function for chars. So are these chars the same? So is the char from provided from the user same as char equal in that they are the same type? Stand them. All right. So like this is like a anonymous function, but I don't get where C is coming from. Like where okay. So yeah, so this returns this anonymous function. Okay. So we're not, this isn't a Boolean, it's a, yeah, okay. It's an element. It's a function that takes an element and returns a Boolean and evaluates to a Boolean. A more proper way to say it. Okay, so next, so this is scoped for these blocks. Length of string, so we're getting the length. This is from their library, I assume. A loop. So we're calling it empty accumulator list. Last position, current position. If the position or current position is -1, then substring sub. Sub is a function that takes a value t, a position, and a length. So position is -1. Current position will be 0. Length will be last position. And we're adding this, or appending it to the front of the accumulator list. Substring. Okay. Yeah, we're getting the substring. And this. Yeah, how long is the substring, which would be the last position? Okay, yeah. Makes sense. And then we're appending it to the accumulator list. Okay. Else, if the position is not -1, so yeah, this would basically if you if if you give a empty string, the position will be -1 here, because the length would be 0, -1 would be -1. So we go down this path, and essentially this evaluates, this sub will get a substring of an empty string, which is an empty string, and append that to our accumulator list. Okay. Else if is delim, here we're applying is delim to string dot position. Now I didn't know you can index into strings this way. Like, I familiar with, like, if you had a string was a array, then it'd be with the parentheses, not square brackets. But this isn't really, we're not dealing with mutable data here. So maybe this is the way you index a string if you're just reading. Yeah, so we can access the character position of a string. Huh. So yeah, strings, unlike other languages where, like in C++, you have strings, but they're implemented underneath as arrays, so you can index into them. But in OCaml, strings and arrays are distinct types. Are treated at least they're treated as distinct types. Yes, arrays are mutable, strings are not mutable in OCaml. And so yeah, they just basically have this difference here to make it apparent that we're not dealing with mutable state. That's interesting. That's a new thing I did not know. So we're essentially getting the character at position, and then yeah, oh okay. Now it's making more sense. So this is the character here that we're passing in, essentially. So we're matching on, so we go through this path that we're using the split function, and basically checking if the character is equal to the the on character that was provided when we called split. Gotcha. All right. So that's else if. So we do all that. We determine if a character is equal to our on character. And if that's the case, if this evaluates, or this instead evaluates true, then we do this block of code where we increment position. We save it in a new variable, position1, and then we scope it to the next escape statement. And then we're getting a substring again, similar to what we did over here when we had like a -1 position. But this is a valid path where we don't have an empty string. So we get the substring from position 1, which is position +1. And then the length from the last position to position 1. And then that is scoped in loop here. So yep, this is a recursive function. Makes sense for it to be called loop. And then pass in the accumulator, so we're not yet oh, right here. Sorry. Loop. Here we are modifying the accumulator. We're not modifying it, but we're creating a new accumulator that has the substring at the head. Pass in the position, which will become our last position, and then our next current position will be the current position -1. So eventually we'll get to a position of 0. So let's go back to this. So if this evaluates to true, we do this, then path. If is dilemma evaluates to false, then we do this else path. We recursively call loop again. We do not do anything to our accumulator, so we pass it through. Last position, this is last position remains our last position. And we decrement our position to be the current position for the next recursive iteration. So these two paths, since they recurse, this has to be met at any time. So this is basically this is our base case, or this is our base case. So position is -1. Okay. Yeah. So position is -1. So we want to add that last character from position 0 to our last position. And then add that to the accumulator list. So the thing I was stuck on was, is this going to add how does this prevent adding a empty string to the head of the eventual product that we're forming here, this T list or string list. And it seems like that's prevented because when we reach this condition, we still need to append last position because it's lagging behind a little bit. Okay. It's lagging one index behind in terms of forming the substring. So, okay. Yeah. Interesting. Cool. Okay, what else? That took a while. Just trying to understand everything to the fullest extent. This is a function that capitalizes the first element or first character of a string. Or of a line, sorry, which is a string. And so we're using pattern matching. We split on the each comma. So you can use like a CSV, a comma separated value type input. And then we match this. It returns a list that has more than 0 elements. Then we define up head, which is the uppercased head or uppercased first character. So we capitalize that and then scope it to this line where we are going to reconstruct our string by concatenating it with commas again. Just like that. And this this is, from what I read, is essentially for this would never be met, but we get that pattern matching is not exhaustive warning without it. And the reason this is not met is because string split, like we mentioned before here, let's see. So string split calls the split gen again. And then this line right here, this is the reason. So if it's empty string, our position will be 0, -1. So it will fulfill this condition and therefore cause this to evaluate. So we get a substring of empty string, which is a empty string, and it adds that to the accumulator list, and then that's what split gen and split evaluate to. So in any case, in any situation, you're never going to have this empty list. You're always going to have at least one element, even if your list is empty. So yeah, I'd like to learn a little more about like assert, or how it's implemented. But that'll be for another day. You could see how string capitalized, string concat is implemented. Yeah, here I basically have a list of string evaluates to string methods. Like I don't think I can have, I'm quite certain I can't have a different typed function within the same list, because then it'd be a different type within a list, which you can't have. So then with me trying to add string split, we get a type error. This expression has type string, but an expression was expected of string and the type of this split function. So that's why I don't have that within our transforms variable. And then this executes, this is something I learned today, is if you lead with the underscore, then it will automatically execute when you run your function. So that's what happened here, or when you run your program, the function will execute. So you can have like multiple of these. We'll just call something else to be. Well, actually, let's just call it the same thing. I'm curious. But yeah, we get it executing twice essentially there. We did that. All right, so here we're mapping through a list. We provide a anonymous function that is pipelined. So basically, so we provide our transforms. So we're mapping through this list of string transformation functions. So we'll basically start with this element, string uppercase, and that will be the argument for f here in this anonymous function, which you can see here is a string to string. And then it applies that function here to this string. Hi, my name is Paul. And then the evaluation of this is then pipelined. What's the real name for this? Reverse application operator. So reverse applied to std.io print and line. So basically, you can imagine that this is kind of, normally you'd have it be like this. So this evaluates, and then print online is applied, and you wouldn't have this here. Basically, you could do this, but it looks prettier in my eyes, at least, having that pipeline operator. So yeah, that's about it for that. Let's just take a peek at string capitalize. I'm just curious. So standard lib. So base is basically a standard library built upon the OCaml standard library that's used in the professional setting. So here we see it's referring to the standard library itself. Standard library string module, capitalize ASCII. So it's essentially the same. Yeah, it's just wrapping the standard library function. All right, yeah. Let's see how that's actually implemented. So here's the standard library version. So we pass in a string b. So there's some module named b that has a function capitalize ASCII. Baz. Oh, bytes. String to bytes. So this must be like bytes, the bytes module. And we return bytes as a string. So Baz converts a string to bytes. Bytes, BTS converts bytes to a string, back to a string. Just let's keep going down the rabbit hole. All right, so this capitalize ASCII within the bytes module takes in the string bytes. Apply 1. We're applying this function here to this. So I'm guessing what this is doing here is and this is evaluating first. No. This is evaluating, but this is being passed in as a char evaluates char function. And then these are our bytes that we're passing on through here. So apply 1 if length of string is 0, then bytes to int. So this is a special length. This isn't your normal string length. This is bytes length. If the bytes are 0, then we just return the string unchanged. Else we can copy string bytes r unsafe set r, and then we're returning r. Where are we applying? Oh, we're applying f here, which is this char uppercase ASCII. I'm not familiar with begin and end in this context. Like I'm familiar with. I think this is syntactic sugar for something else. Unsafe get takes in bytes and an int, which is 0 here. Returns the char. Wonder what int is. does not say. We apply this to the, okay. Yeah, I haven't learned anything about handling bytes in OCaml. So this will make more sense in the future. It's good to take a look at it though. Because from what I understand is we're still applying this char to uppercase. Oh. Is this the index? And it's got to be the index, the first. Let's figure that out. So unsafe get S0 gets the first char of the string S. F is applied to that char character. Yeah. So we get the first character in bytes. We apply. Right. What does this evaluate to? No, we get the char, and then we apply uppercase ASCII to that char. But this is bytes, so get unsafe. I might as well ask. Oops. So in OCaml, the function is prefixed with unsafe or low-level operations that skip bounds checking and assume you know what you're doing. Okay. They avoid the runtime cost of checking that the index is within bounds, but you can get unbehind behavior if you're not implementing it correctly. Okay. Whew. All right, back to our example we're working on. What else? I assume uppercase, or what do we do? Capitalize? I assume these all work essentially similar. Let's just go to uppercase. Yeah, okay. And uppercase ASCII. Yeah, similar, except for we don't need this apply one function here. We can just map through the characters of the string and capitalize each or lowercase each. Okay. Forgot to look at these. Let's see. So here the char module, lowercase ASCII and uppercase ASCII. So we have a pattern matching. Okay, so this is looking regexy. So A to Z. So any capital letter from A to Z as C. Unsafe. Char. Get the code. And this is all, yeah. We return that character. Okay. Because of, what is it? So capital A is in ASCII is equivalent to 65. If you add 32, we get 97, which is lowercase a. Let's go to the ASCII. Lowercase a is 97. Yep. All right. So that's what we're doing here. We're shifting essentially. We're shifting from capital A or whatever capital letter you provide and shifting it to the lowercase counterpart. If it's not a capital letter, then we just return the letter. Or yeah, if it's a lowercase lowercase letter, then we return it unmodified, and then we do the opposite here for uppercase ASCII. Ooh. What else? String concat. You can look that up. So we have a optional separator that is defaulted to a empty string. But you can have like a comma for comma separated values. All right, so we're matching the string list. It's empty, return empty string. The standard lib does not specialize this case because it could break existing projects. In any other list, we will use the standard lib implementation. Okay. So this is just I'm guessing a performance boost by adding this case here. Because if you didn't have it, you're still fine. It's just by adding this, you don't have to actually call the underlying standard library string concat. Yep, we're passing in the separator. Let's go to this. So concat takes a string separator, string list, and we're pattern matching again. If the list is empty, then we return an empty string. Otherwise, we're sep length. BTS, and then we're appending. And for very long strings, this would be problematic, I think. I know this is linear time versus it's not a constant time operation. You're appending to the end of the list. Let's see. Sum of lengths. Let's see. Okay. I don't know what I'm doing. So essentially what that's doing is getting the sum of these, and then it's getting the length of this and summing all three of those together. And then create bytes from its. Create n returns a new byte sequence of length n. And chars are usually, they're 1 byte in C, so that would make sense. You'd only need to create I gotta see what the underlying implementation of bytes is, but yeah, you'd only need 1 byte per char, which would be your sum of lengths from the list that you've still have to concatenate, and the separator, and from the start. Yeah. Oops. And then what were we doing here? So unsafe. Alright, let's see what this is though. These must be arguments. Yeah. String. Oh, right here. So recursive function. It's going to get a rough idea of what this is doing. So unsafe blitz is a high-performance string or bytes concatenation routine that joins the list of strings together with a separator, writing directly into a pre-allocated destination buffer dist. I'm guessing we're returning dist after, once the list is finally empty. Each time this is recursing, it's going to somehow modify dist. Maybe it does in this. It's more performant because it skips bounds checking. so we've pretty much gone as deep as I wanted. We could do like list map. Maybe I'll save that for another day. It's getting kind of late. How long have I been streaming? Just over an hour. Anything else I want to touch on? Here's where I was reading about the pipeline operator. Now it's left associative. So it goes from left to right in evaluation. Is there another? Here's that application operator that we saw here, maybe? Where? Here. Which is right associative, right? Yep. Right associative. So yeah, this is being evaluated first, and then this is evaluated. So instead of having this chunky parenthesis mess, you can have a streamline. This evaluates, then G evaluates, then H evaluates. H evaluates here, then G evaluates the product of that. Ooh. I think we put in good work today. All right, I'm gonna call it. All right. So I hope you guys have a good day or good night whenever you guys watch this. It's been pretty productive. So I'm pretty happy. All right, see ya.